Hello everybody, welcome to today's video. Thank you very much for joining, my good friends. So today I'm going to introduce a new chapter of the book we have been exploring. It is the Physics for Scientists and Engineers by Surway and Jowett, chapter 24, the electric potential. So this is a little bit of a different style of video than the previous couple of videos I've been doing. And it's going to be kind of a lecture sort of video. I'm not going to solve too many problems. I'm going to introduce some concepts, some resources, and some equations just to get you guys a little bit, I guess the word I'm looking for is acquainted with this new thing called the electric potential. So we're going to look at today's contents. I have them listed out over here just because I think the video might be a bit long. So I'm going to start off with this online resource for people that are curious about physics. You can take a look at it. It is free. It is called the Feynman Lectures on Physics. So you can take a look at this online. I'm actually going to start the video off by introducing a little bit of this and talking about the gentleman that created it, Richard Feynman, the GOAT. The next thing we're going to look at is a small review of the dot product, the vector dot product. So this is also referred to as the vector scalar product. You may have seen some of this discussed in a couple of my previous videos, like the Gauss law includes the dot product. But the reason I'm introducing this is because of point number 3, which is the introduction of work. So the word work in a regular day-to-day life, just refers to going, getting a paycheck, working out, maybe doing work. But in a physics, the definition of work to a physicist is a little bit different. So we're going to introduce that, and it actually uses the vector dot product, which is why I first start off with point number 2. And then we're going to see what electric potential energy is for point number 4 and how it can lead to the electric potential. So I think these last couple points here about work, potential energy, and electric potential, they're going to be the main sort of things that you use in this chapter 24 on the electric potential. So I'll start off with talking to you guys about the Feynman lectures. I have a couple of pictures of Richard Feynman over here. Take a look at this guy. What a beautiful dude. He lived in the previous century, 1900s, and passed away sometime in the 1980s, if I'm not mistaken. A couple nice pictures of him here. Here's a quote. I'm not too sure if he actually said this. I didn't fact check it. I just took a look at some pictures on Wikipedia. And he says, "As I get older, I realize being wrong isn't a bad thing like they teach you in school. It's an opportunity to learn something." So the reason this guy's a GOAT is because he had a fantastic way of looking at physics and science. He had this other famous quote where he says, you don't have to be born, you don't have to have a special attribute, you don't have to be born with like a special quality to be a good physicist. You can be a regular person, a regular, normal, average IQ person. And he says, that's what I was. I, like Richard Feynman. And the reason he says this is because he won a Nobel Prize sometime in the 1960s, I believe, and he did some insane work on quantum mechanics, specifically quantum electrodynamics. I actually have his Wikipedia page open here. So let's take a look at it. Richard Feynman, you can see here, he is known for the work he did in the path integral formulation of quantum mechanics. This is crazy because in the 1900s, quantum mechanics started getting developed in the first sort of a couple years. So I think in 1905, Albert Einstein started talking about what was it called? The Brownian motion, the photoelectric effect, a bunch of things that they first introduced to you once you start learning quantum mechanics. And then in about 1920, 1927, quantum mechanics as we study it today in school was fully formulated, and everything that you kind of learn in introductory quantum mechanics, they finalized in like 1927. Then around the 1930s, 1940s, 1950s, all those years there, they tried to combine quantum mechanics with Albert Einstein's theory of relativity, which was kind of a different way of looking at gravity. And when you combine all of that together, you get this new kind of field of physics called quantum field theory. And this guy, Richard Feynman, is one of the pioneers, I guess, of a specific branch of quantum field theory, which is called quantum electrodynamics. Basically, he took the course that we're looking at today, um, electromagnetism, and he said, how do we apply quantum mechanics to this? And okay, I am back. I just had to cut off the audio for a second. So what I was saying here is, yeah, this guy is a solid physicist, and the reason I'm bringing him up is because he did a couple of lectures on physics. He was a professor, and if you search up on Google the Feynman lectures on physics, you will find this page over here, probably the top link. This is a phenomenal resource for any kind of student studying physics because he has these 3 volumes. They are also published in actual textbooks, but here you can find everything online for free. So volume 1 has a whole section on mechanics, radiation, and heat. Volume 2 is electromagnetism and some points on matter. And volume 3 is all of quantum mechanics. So let's open up just one of these to take a look. I'm going to click on volume 1. And if you click expand all, collapse all, you can see all the little chapters here. What I wanted to show you guys, well, first of all, you can take a look at this on your own, read through it. It's pretty interesting. You can see all the chapters here. But I wanted to go into this section on mechanics. You can see here, chapter 4, they have a point on conservation of energy. And they also have a section on potential energy. So if we scroll down here a little bit, we get to conservation of momentum, vectors, very nice thing to take a look at if you are struggling with vectors. Characteristics of force, work, and potential energy. So this section here introduces potential energy, and it is kind of an important concept because in classical mechanics, you normally get introduced to potential energy, and it becomes a framework that you can use in a lot of like physics classes. So that's why this chapter 24 on the electric potential is a little bit complex, because it uses certain parts of work, potential energy, stuff like that, that you're not really reminded about when you're studying this class, electricity and magnetism. So I wanted to just first of all show you this text because you can look at any of this, read it. It's a pretty cool section, but I'm going to dive into this section here, chapter 24, work and potential energy conclusions, just because I wanted to read a little bit of the things this guy talks about to kind of help you out, or, you know, just to show you some interesting stuff. I'm not going to read all of it. You can take a look at it on your own, but I want to start off today's video with this. So normally once you click into a chapter, they show a couple of pictures from the actual lectures he did. So he drew on a chalkboard. And then here they have a couple of sections. So I'm going to go through a bit of this stuff here. You can also click this little side section over here. Oops. And if you click on this little recording, he actually posts recordings of the actual lecture. So you can listen to that and hear what he says. He basically goes over the content that he writes here. So I just want to read out a little bit of the stuff here to show you the way this guy thinks and to, I guess, just outline a couple of interesting points. So he says in chapter 14, in the preceding chapter, we have presented a great many new ideas and the results that play a central role in physics. These ideas are so important that it seems worthwhile to devote a whole chapter to a closer examination of them. In the present chapter, we shall not repeat the proofs or the specific tricks by which the results were obtained, but shall concentrate instead upon the discussion of the ideas themselves. So this second paragraph is what I want to show you guys. In learning any subject of a technical nature where mathematics plays a role, one is confronted with the task of understanding and storing away in the memory a huge body of facts and ideas, held together by certain relationships which can be proved or shown to exist between them. So basically a lot of equations and stuff. It is easy to confuse the proof itself with the relationship which it establishes. Clearly, the important thing to learn and to remember is the relationship, not the proof. In any particular circumstance, we can either say it can be shown that such and such is true, or we can show it. In almost all cases, the particular proof that is used is concocted, first of all, in such a form that it can be written quickly and easily on the chalkboard or on paper, and so that it will be as smooth looking as possible. So what he's saying here is the equations that you see in these books, normally some people have worked on them and they have created this form that looks pretty simple and you can just write it on the board really quick. And the thing he was saying in the first part of this paragraph is, you don't have to remember all the proofs or all the how this comes about. You just have to remember a couple of the ideas that are used to get to it and the actual equation itself, what the equation means. So then he goes on to say, consequently, the proof may look deceptively simple when in fact the author might have worked for hours trying different ways of calculating the same thing until he has found the neatest way so as to be able to show that it can be shown in the shortest amount of time. The thing to remember when seeing a proof is not the proof itself, but rather that it can be shown that such and such is true. Of course, if the proof involves some mathematical procedures or tricks that one has not seen before, attention should be given not to the trick exactly, but to the mathematical idea involved. It is certain that in all of the demonstrations that are made in a course such as this, not one has been remembered from the time when the author studied freshman physics. Quite the contrary, he merely remembers that such and such is true, and to explain how it can be shown, he invents a demonstration at the moment it is needed. Anyone who has really learned a subject should be able to follow a similar procedure. But it is no use remembering the proofs. This is why in this chapter we shall avoid the proofs of the various statements made previously and merely summarize the results. Okay, now I just want to talk to you guys about work, which is the next point we're going to get into. And he does kind of a nice sort of summary of the work here. So I'll read out this final thing and then I'll stop reading this text. You can go on and read it on your own. Maybe I'll put a link in the description. So the first idea that has to be digested is work done by a force. The physical word work is not the word in the ordinary sense of workers in the world unite, but is a different idea. Physical work is expressed as this integral quantity here. So it is written as integral vector f. You can see it's a vector because it's bold. And then the dot, which is the dot product there, ds, where s is also a vector and it means like displacement. And the little d there means a super small displacement of the s. So you could say differential displacement. So he calls this the line integral of f dot ds, which means that if the force, for instance, is in one direction and the object on which the force is working is displaced in a certain direction, then only the component of force in the direction of displacement does any work. So I'm going to stop right here, and you can see how I kind of split apart today's lecture into these couple points here. First of all, I wanted to introduce the Feynman lectures. You can take a look at those, read them, listen to the audios as well. Also, another cool video that you can take a look at on YouTube is Feynman's explanation of fire. You can just search up Richard Feynman fire on YouTube, and one of the first videos there should be cool. He basically explains how he sees fire or the reaction of combustion. It's pretty cool, very interesting. It's like, I don't know, 5 or 10 minutes. And then I wanted to go into the review of the dot product and then the review of work. So the reason I talk about work is if I pull up the chapter in our textbook over here, so we have physics for scientists and engineers. I'm going to go over here to chapter 24. You could see the chapter starts off with electric potential and potential difference. And they actually start the chapter off over here by saying work, you can see this equation here, work with the subscript int, like internal work, is equal to force times distance. And in the case for the electric field, they replace force with this QE, which I'll get to in a section, or in a second. Then he talks about work and potential energy, and then they introduce this equation here, which is the equation for electric potential energy. And then they finally define electric potential or electric potential difference, which is the main section of this chapter. So after that, they lead into some points about work. They introduce some units. They actually also define the electric field in terms of the electric potential. So they say the electric field is a measure of the rate of change of the electric potential with respect to position. Might sound a little bit crazy, but you'll see kind of where we're heading at. This is why I wanted to introduce work before we get into this, but I'm just showing you guys a bit of the section 24.1. Then in section 24.2, they start using the equation that they introduced here for potential difference or electric potential difference. So before we get into that, I wanted to introduce the dot product to you guys. And if you take a look at the contents of this chapter, we have chapter 4, which is what I've been focusing on mainly, chapter 22, 23. Now we're getting to chapter 24. If we take a look at the first section of this book, there is a part on mechanics. So here we have a lot of kind of content from classical mechanics. And over here, we get to energy of a system, conservation of energy, and stuff like that. So what I want to look at is chapter 7 on page 150. So I'm going to jump to there, which will be my introduction on the dot product and on work. So here it is, energy of a system. You can take a look at this chapter 2 if you want. It deals with a bunch of stuff, but basically how it starts off is work done by a constant force. They introduce work over here. The work W done on a system by an agent exerting a constant force on the system is the product of the magnitude F of the force, the magnitude delta R of the displacement of the point of application of the force, and cosine theta, where theta is the angle between the force and displacement vectors. So they have equation 7.1 here. I think in this chapter they also give a brief explanation of the dot product. The scalar product of two vectors, section 7.3. So here it is. I'm going to just read out this section. Because of the way the force and displacement vectors are combined in equation 7.1, 7.1 is work equals force times distance times cosine of the angle between them. It is helpful to use a convenient mathematical tool called the scalar product of two vectors, scalar product or dot product. We write the scalar product of vectors A and B as vector A dot vector B. Because of the dot symbol, the scalar product is often called the dot product. The scalar product of any two vectors, A and B, is defined as a scalar quantity equal to the product of the magnitudes of the two vectors and the cosine of the angle between them. So you can see here equation 7.2. We have the dot product on the left-hand side, A dot B, and you can tell A and B are vectors because they are bold. Normally, we bold vector quantities, and they also have a little line on top of them, which means they are vectors. On the right-hand side, you see A dot B, A times B times cosine theta. A and B are now not bolded and they don't have a vector on top of them. So what A and B refer to on the right-hand side is the magnitude or the length of the vector A or B. And cosine theta there is cosine, the cosine function, which you've learned from trigonometry. Theta is the angle between those two vectors. So normally how I draw this is, let's say I have a vector here, this is vector A, and a vector here, this is vector B. This would be the angle theta between them. And these vectors can be pointing in any direction. They could be pointing like this. This would be the angle between them. So yeah, the dot product here is written like this. And it is also called the scalar product because you can see here we have a scalar times a scalar times a scalar. Scalar is just another way of saying number, not vector. So you can distinguish vector and a scalar. They are two separate things. A scalar is just a number. You could say just a magnitude, and a vector has a magnitude and a direction. Cool. So now that we've introduced this, they go back to the how you use the dot product in the definition of work. So they have this definition over here, right? Work, which is a scalar quantity, work does not have any direction. It has units of joules, or sometimes it has units of, it has units of Newton meters, right? Because here we have force, which is in units of newtons. Here we have displacement, which is in units of meters. So we have newtons times meters, Newton meters. And since this is a dot product here, you can use this dot product identity to split up the equation for work into the magnitude of the force vector, magnitude of the displacement vector, and cosine of the angle between them. All right. So before we move on to actually defining work, I'm going to show you guys how I think about this. This is an example I've shown in classical times. So let's just recall that the dot product is A dot B. Let's draw this a little better. B is equal to A. Normally they write the magnitude with these vertical lines around A, and B, the magnitudes of these two things, right? Because normally I don't bold things when I'm writing. It just takes a long time, so I just denote vector with this thing here. So AB, cosine of the angle between them, right? And this is just a mathematical tool, but how we can use it in physics is we define this thing called work, which is force times distance. Let's say distance is this. Let's call distance x, and both of these are vectors, okay? So how we can expand this is force magnitude of this times displacement or distance, which is x, and then cosine of the angle between those two guys. So think about work being the force applied to some object. So the example I use a lot is you're in the mall and you have a shopping cart like this, and you want to push the shopping cart down the aisle a distance x away. So you want to push the shopping cart all the way here. Let's say this is the displacement vector, x. And the way you do that is you apply some force like this, force. So in this case, the work done on the shopping cart, this is how you talk about it. You are applying work onto the system, which is a shopping cart. You know, in classical mechanics problems, you might see a block on a table like this and you push it, or you might see some block on an inclined plane and you push it up. So this is like classic problems that they ask, and they ask you to calculate the work done to get the object up. So with the shopping cart example, literally all you do is force, let's draw this in red because the vector is red, force and then dot distance x, and then I'll do times again cosine of the angle between them. Now take a look at the angle between them. Let's say I were to expand this force vector so that it is over here, right? This is just me expanding the force vector. It's right here. What is the angle between these two guys? What is theta? Well, they're pointing in the same direction, so the angle is 0 degrees. Now, if you remember the cosine function looks like this. Let's say over here we have cosine of theta, and over here we have theta. So cosine of 0, which is right over here, is actually 0. The cosine function starts here. And then if you move, oh, my bad, I actually made a mistake for cosine and sine. Cosine of 0 over here actually is 1. So the cosine function is blocked between the values -1 and 1. You can plug in the cosine function in some graphing calculator or take a look online. And the cosine function starts over here at 1. It starts decaying until it reaches 0, and then it reaches -1 and then bounces back. This is a classic cosine function, and then it repeats itself. So normally the units that you use here are radians, which kind of expresses the angle in terms of pi, 2 pi, you know, radian quantities. But in this case, we have degrees. So we have over here 0 degrees. Over here, where the cosine function is 0, is at 90 degrees, or pi over 2. Over here, where the cosine function is -1, it is 180 degrees. Over here, it would be 270 degrees. And then over here, we get back to the original spot. You know, the function starts here and it ends here, and then it starts repeating itself. This would be 360 degrees, which is interesting because if you call two vectors like this pointing in the same direction at 0 degrees, once you go all the way around the circle, this 0 degrees and 360 degrees is the same thing. So cosine of 0 degrees and cosine of 360 degrees is both going to equal 1. So all of that is to say that you can simplify this equation here by plugging in cosine of 0 degrees over here, and this entire thing here equals 1. So the whole work equation simplifies to force times displacement. Sometimes this x displacement is written as d, and you can get the simple equation work equals force times distance. So this is normally how they introduce work in a lot of classical mechanics courses, but the important thing is that the full way of writing it is actually force dot product displacement. And the reason this is the case is because it takes into consideration the angle between these two vectors. So I wanted to show you guys the scenario where that is actually taken into consideration. So let's say we had the shopping cart like this, and normally when you're pushing a shopping cart and you're standing like this, you are not applying a force vector that is exactly in the horizontal direction. You might be applying a bit of a force like this, right? So if you are applying a force like this, let me draw a more clean looking vector like that. You're applying it in some kind of direction like this. So maybe you're resting a bit of the weight of your arms on the shopping cart. You know, you're putting your arms a little bit pushing down, and you're pushing a little bit towards this direction, and the cart still moves forward. So you can break apart this vector using components. And how you can break it up is this over here will be the Fy. It's going in the negative y direction, but you can call it Fy component. And this over here is the Fx, while this big red vector is the total force vector. Total. So this is how you break apart a vector into its components. Maybe you're given some angle over here, or maybe you're given this angle over here. And if you're given those, you can use SOHCAHTOA to break apart vectors. I've talked about that in some previous videos. So now the shopping cart still gets displaced by this vector, which we can call x. Actually, let's change it to s, just to show you guys that you can call force, distance by any kind of variable, as long as you kind of stick with it. So I'm going to call it now s instead of x, which means displacement. This means maybe distance vector, or sometimes they call it displacement vector, right? It is just a vector. So now, since we have the force broken up into components, it is natural to talk about the work in the x direction and the work in the y direction. Now, this is still force times distance, except the force that you have to take into consideration is the force in the x direction and the displacement in the x direction, force in the y direction, and displacement in the y direction. In these cases, you don't have to apply the cosine theta over here and over here. And the reason is because the cosine theta is there in order to break apart stuff into its components. So if we've already done it, there's no need to do it. You can just work with components. And I'll show you kind of where the cosine theta kind of comes into play a little bit later. So if we expand this, you can see that this distance here is all in the x direction. So we can call this displacement s subscript x. And what we get for this work is literally force in the x direction, which you can calculate. It is this vector over here, and displacement in the x direction. So this will give us the work in the x direction. Okay, looks pretty good. Now, if we go to the y direction, we still have a force in the y direction. This is kind of the weight of your hands pushing down onto the cart. And the different thing here is that the shopping cart cannot move up or down. There is no displacement in the SY direction. It is blocked by the floor, and the cart is not going to fly up any direction. So the displacement here, SY, is actually equal to 0. So you multiply 0, and you can see actually that the work done in the y direction is 0. So that is a little bit of a difference here between the two components. When you have a vector that is pointing in a different direction than your displacement vector. So remember how over here I expanded the force vector? So originally it was written like this, and I just expanded it over here just to see the angle between this x vector and my force vector. I saw that they were pointing in the same direction, so the angle between them is 0. And when I plug in the angle between these guys, I get cosine of 1, and I just get force times distance. Force times distance. In this case, what I got for this case is the same thing, force times distance, but in the y direction, I got 0. So this is what the dot product does for you. If I take this force vector right here, and I just shift it over right here to see the angle between the two vectors, I haven't changed the direction or the magnitude of this vector. I just shifted over. I can see that the angle between these guys over here is theta, and this does not equal 0 degrees. It equals maybe something like 30 degrees or whatever. Let's just say it's theta. What I've done here is everything that the dot product does for you. So if you have the original equation for work is equal to the force dot product, the displacement vector S. You can expand this as force, magnitude of force, S, magnitude of S, the displacement vector, times cosine of theta. If you plug in cosine of theta is equal to, let's say, in this case, it was 30 degrees. Cosine of 30 degrees, if we look back at this graph over here, let's say it was 30 degrees. I mean, this angle here could be anything. It's not going to be 90 degrees because 90 degrees is going to be if they're facing like that. And it's not going to be 0 degrees because 0 degrees is when they're facing together. So it's something between 90 and between 0. Let's just say 30 degrees, right? It could be 45, it could be whatever. 30 degrees is somewhere between here. So let's say, this is 0, this is 90. Maybe it's right here. So we take a look, and it is something over here which is a little bit below 1, right? This function is somewhere below 1, but it's also above 0. So let's just say, I don't know, actually, we can plug in cosine of 30 degrees. So I've actually calculated cosine of 30 degrees, and it's a square root of 3 over 2 exactly, which is about 0.866. So the interesting thing here is that this dot product, like I said before, once you do it fully with the full magnitude of the force vector and full magnitude of the displacement vector, it basically does this decomposition for you. And if you work that out, you can see that, well, if I bring back my original force vector here that I tried decomposing into x and y, the angle theta is technically exactly equal to the angle between f and this x over here. That is, if I take these two and slide it over, you can see that it fits perfectly right there. So those angles are the same, right? So the dot product is a way of decomposing which component of the vector points along into the same direction. And it's very, very useful because it is used in a lot of places for physics. So if you take a look at my Gauss law video, Gauss's law is an equation for electric flux, and it tells you that electric flux is equal to the integration over this quantity, E dot dA, A is a vector, and this integral here just says add up all of these components. And what these components mean is, well, this is just the standard electric field vector. So this is like some electric field line going in some direction. And this dA is the normal vector pointing out of your Gaussian surface. So normally how I introduce flux is, let's say you had a side of a box right here. Let's say the box was like this, right? And on this surface, the dA vector would be this. It is perpendicular to the side of the box surface. The dA vector here would be facing this direction, dA. On the bottom side, the dA vector is pointing here, and on this side, the dA vector is coming out and pointing straight towards us, the viewers of the video. So if you had an electric field which was going like this, it is entering the left side of the box, and it comes out here like this. Well, this dot product here is telling you take the component of the electric field vector that is pointing in the same direction as the dA vector. So over here, you can see the dA vector is pointing in the same direction as the electric field. So E dot dA over here is going to be maximum. It's going to be literally equal to E times the magnitude of dA, because cosine theta here, well, theta, the angle between these two vectors, is 0 degrees. So cosine of 0 degrees is equal to 1. In this top surface, and what I was saying here is the flux, the electric flux created on this side of the wall is going to be maximum because they're pointing in the same direction. If you take a look at this side of the box, the electric flux is going to be at a minimum because the electric field line is going like this, while the dA vector is pointing like this. So in this case, the angle between these guys is 90 degrees. And when you take the dot product and you expand this using the dot product, magnitude of the E vector, magnitude of the dA vector, cosine of 90 degrees, this is going to equal to 0, right? Plug it into your calculator or just take a look at the function I drew here. The cosine function starts at a maximum value when theta is 0, it equals 1. And then it decays until it reaches a value of 0 when the angle inside of it is 90 degrees. So the dot product is used over here in Gauss's law. It is used over here in calculating work, and it is used in multiple other cases. So that's why math and physics kind of intermingle very nicely, because the dot product originates from a mathematical identity of basically just multiplying vectors together. Okay, now that we've talked about that, and we've talked about the dot product, and we've talked about work, I'm going to talk about work in just a little bit more detail. So work is equal to force dot displacement, right? And over here, what I showed you was a displacement of Sx along a straight line, right? But let's say my shopping cart was going along some weird path like this. Then how do I calculate the work? So what I'm going to do here is basically draw a weird path like this. I'm going to call this, again, the S vector. And let's say I had, a force. I'm pushing along this direction. I want to calculate the work done over this entire path. But if my force here is constant, it's pointing in the same direction, then you can see if I take the dot product of, for example, this part with this force vector, the angle between these two guys is pretty much 0 degrees. They're pointing kind of in the same direction, so maybe it's like 1 degree. So the work done over here is going to be maximum. But then once I get to this part of the path, the S vector is pointing in a different direction here, almost 90 degrees. I mean, maybe in this scenario, the S vector and the force vector, they are going to be at 90 degrees. So the work done on this part of the path is going to be 0. Meanwhile, here it's going to be a maximum. So over here, we get back to the original case. The S vector points in this direction. The force vector points in this direction. Theta is pretty much 0 degrees. So the work done on this part of the path is again going to be maximum. Here, again, we reach a minimum value, right? Because the force vector and the displacement vector are at right angles. And you can see each part of the path, it has a different kind of value of work that is being done. So you can't just use this equation here. And what you actually have to do is you have to break apart this entire line into tiny little differential quantities, which we will call ds vectors. And this is kind of the use of calculus. So you can thank good old Newton and Leibniz for inventing calculus. And since we're breaking down the s vector like this into little ds's, we will again also break down the equation into little ds's. Oops. We are going to break it down and just write a little ds here. And if we want to find the total work, we literally just have to take an integral, which is a summation from over here, the starting point. So maybe I can call the starting point A, until here, the ending point. So maybe I can call that B. So this is an interesting kind of integral. It's not like the classic integrals that you see where you have a function here, y, you have a point A and a point B, and you find the area between this. This would be written like this, from A to B. This is kind of the integral that you see first hand in a calculus class. The integral here is a slightly different one, and it is called a line integral. Not too important. The only important thing is how you can use it in this equation here. So you can find the total work done using this integral here. And it's actually very cool because it looks super similar to Gauss's law. You see Gauss's law also has this integral, except Gauss's law has this little circle, which means a surface integral. So here we have a line integral, here we have a surface integral, and those are actually quite advanced calculus topics, something you learn in Calculus 3 if you take it. You will not learn about surface integrals and line integrals if you take Cal 1, Cal 2. And that's why this E&M course and a lot of physics courses are slightly complicated for students first taking a look at it, because you learn about the physics and then you apply mathematical concepts that you haven't even looked at before. So I'm introducing them here just to show you guys that they are introduced later when you take math, but it's not too important to actually know how to do the integral. The main important thing is to know that this is basically work is equal to force times distance. Again, you have to know why this integral is here. You have to know why this dot product is here. But the main equation is still work equals force times distance. That's the same thing with Gauss's law, actually. If you remember Gauss' law when it was first introduced, let me erase this whole picture. Gauss' law was literally introduced as the quantity electric flux is equal to magnitude of the electric field going through some area. Flux is equal to E times A. And then again, you do the same kind of breakdown that I showed you here. You have a dot product, you decompose this A into a small differential quantity A. Both of these have directional components, so they're vectors. And since you have a dA here and you broke everything down into super small quantities like these guys, you want to find the total electric flux. So here, total. You take a integral over the entire surface. So flux is a quantity that talks about surfaces. That's why you take this surface integral. And again, you don't have to know how to solve crazy integrals like this. You just have to know what electric flux is. It is electric field going through some area. You don't have to solve crazy integrals like this. You just have to know work is equal to some force applied over some displacement. And I'm showing you the integrals here because they're quite important. You know, you won't have to solve these. Like I said, they're crazy integrals, but you just have to know why it's written like this, why the mathematical form is written like this. So a final thing that I'm going to introduce before we get into the actual content of this chapter, the electric potential, is there is this relationship between potential energy and kinetic energy. You may have seen it before. This is kinetic energy. If you combine it with potential energy, normally you should have a constant, which is 0. And why I say constant is sometimes they have these triangles here, which means change in either it is kinetic energy or it is the change in potential. And you see this word potential. It is a word that's gonna come up again. But again, first you learn it in a classical mechanics course in terms of energy and in terms of gravitational potential energy, firstly. So this equation here is a very important equation. It is the conservation of mechanical energy. So basically they tell you the world can be split up into two kinds of energy. A kinetic energy, which is kind of like an energy of motion. motion energy. And normally how they write it is K is equal to 1/2 mv squared. Kinetic energy of some object with mass m is equal to 0.5, just a number, times the mass of the object times the velocity of the object squared. So you can find kinetic energy of anything. If your car is going 10 kilometers per hour and it has a mass of like 1,000 kilograms, you can multiply all those numbers together in SI units, and you should get the SI units of kinetic energy in terms of joules. So you can find the energy of an object. Potential energy is a bit more complicated. So since the universe can be split up into these two forms of energy, either an object is moving and it has some kind of kinetic energy, some energy of motion, or the object has the potential to gain motion. So this potential energy is a bit of a complicated concept, and the reason it's complicated is it doesn't have one equation like this. It has multiple different equations based on where the potential energy is coming from. In classical mechanics, you can have gravitational potential energy, which is normally written as U. So normally potential energy is written as U, the letter, and kinetic energy is written as K. So gravitational potential energy normally has the subscript G, and it is the height or the change in height of an object times its mass times the gravitational acceleration. So this is one equation for potential energy. You could also have chemical potential energy, electric potential energy. Electric potential energy we are going to introduce in just a second. You can have magnetic potential energy. They use the letter B to represent magnetic potential energy, or I guess just magnetism. It uses this letter B. You could have chemical potential energy. I'm not sure what that one is, and maybe it's a C here. You can have all types of potential energy. Maybe potential energy due to a spring being stretched. Potential energy of a I'm not sure. Any kind of different form of potential energy could exist, and that's why this equation normally becomes a little more complicated. So, right, this equation here can be rewritten as the change in kinetic energy is equal to the negative sign here, change in potential energy. And the reason that negative sign here is because the summation of these two gives you 0, the conservation of mechanical energy. And you could do the same thing on the other side, which would just put the negative sign here with kinetic energy. So one other thing they introduce is, as you have a change in potential energy, you actually have work being done on the system. So this is something they introduce in classical mechanics, but basically they're saying that the change in potential energy, or you could say the change in U, which is the letter they use for potential energy, is equal to the negative work done on a system. So maybe you can think about this as, how hard would it be to bring this ball all the way up here, a height of h? So you have to change its potential energy, gravitational potential energy in this case. And when you do that, you apply some force times a distance, and you change this ball's potential energy. So these are a couple of important equations. Here we have the change in potential energy is equal to the negative work done. Or if you bring this on this side, you can get change in potential energy plus the work done on an object gives you 0, the conservation of this potential energy work relationship. You have the same thing for kinetic energy. Kinetic energy plus potential energy gives you 0. The classical mechanical energy conservation law. And then again, you have the equation for work, which is work done on an object is an integral over the force vector times this infinitesimal displacement vector. So these are a couple of interesting kind of equations. Alrighty. Oh, also the equation change in potential energy is equal to negative work done on the system. And this you can just get from this first equation if you move stuff on the other side. So now we are going to introduce electric potential energy. I'm going to put in blue change in electric potential energy is equal to the negative work done on a charged particle, which is equal to force times distance, except in the expanded form with the dot product and the integral. And because we have a minus sign here coming from the potential energy work relationship, we have a minus sign here. And finally, if we're talking about electric potential energy, this here will be the electric force due to Coulomb's law. This is the thing that we introduced in the first chapter. So Coulomb's law can be written as Coulomb constant, one charge, a second charge which feel a force on each other, and divided by the distance separating those two charges squared. We also learned that if we divide out some unit charge like this, we can express this force equation using the electric field. So this electric field, we found it by dividing out a Q from Coulomb's law, and we discovered that the electric field can be written very similarly to Coulomb's law, which is Coulomb's constant times the charge creating the electric field divided by the distance from the charge to the location where you want to calculate the electric field, that distance squared. So you can see they look very similar to Coulomb's law. In fact, if you take Coulomb's law here, Fe, and you divide out a Q, then you get the electric field. Which can also be written as the equation I have here on the side. So I hope this little rectangle of equations makes sense. If you can see here, we were actually introduced to Coulomb's law in the first chapter. And then we said, okay, what is the force per charge? The force, if we divide out some unit charge, what would be the force due to some charged particle if we were to place a charged particle at some location in space? So basically what we're saying is we have a point charge at this location, point P. What would be the force if we were to place in this location some charge Q? So that is this quantity force per unit charge, newtons per coulomb. And this quantity we define as this new thing, the electric field. And again, since we define this, we can now multiply this charge Q on this side, and we get a new equation for the force, which I have drawn right here. Okay, I'm going to slide all of this over right here, erase this line, and just draw this, just so you know where it's coming from. So remember, the original thing we were trying to do is find an equation for electric potential energy, and I'm gonna write this over here. This is electric potential energy. It is a new thing we are defining. We're defining it from this equation here. Change in potential energy is equal and opposite to the work done on a system, and the work done on a system is a force times a distance. So kind of new things that we are including. That's why this chapter is a little bit complicated. We're introducing a bunch of new stuff. But now let's rewrite this equation that we had here, the force, and we're going to rewrite the force as Q times the electric field, right? That is the whole tangent I went on down here. And then we're going to rewrite everything else. So E dot product ds. Alrighty, and actually, since we have a charge Q, this charge is not being integrated over. It is a constant. The only thing the integration is integrating over is this ds. And since the ds is coupled to the electric field via this dot product, you can't pull out the electric field unless you make some further arguments. So in the most general case, we can pull out the constant Q on the outside of the integral. Let me draw that Q a little better. And we cannot pull anything else. This is the most general case for electric potential energy. Okay, so now I'm going to take this final form of electric potential energy here, and I'm going to take this original equation, which is how we calculated electric potential energy, and I'm just going to copy it down here on a new equation. Electric potential energy. Change in, sometimes, yeah, you can do change in, which is this small delta symbol. Whoops. Electric potential energy. And by the way, the change in, this little change in happens due to these integration bounds. So remember how I talked to you about this work equals force times distance? The distance is happening over some location here. We start here at a point A and we end over here at some point B. So that is where you see this little change in symbol come from. So, right, now that we've calculated an equation for the electric potential energy, it is also equal to the negative work done. And in this case, I mean, in most cases, we talk about work as a force pushing over a distance. In this case, the force is coming from an electric field. So it's kind of like electric work. But in most cases, when you talk about work and energy, you talk about it in a global sense, like energy and work. Here, since the potential energy is coming from an electric field, we like putting this little E here to just denote it's coming from an electric field. But for the work, we don't really have to put that. Maybe you can do the electric work. Most of the time in the book, they do not have that. So as I showed you guys, the derivation that we did here, sometimes you have these bounds A and B. For now, we will leave them blank just because it doesn't really matter too much. You can leave it general like this. We have this equation here. And if I pull up the textbook over here and I go to chapter 24, this is the first equation that they show us here. Change in electric potential energy of a system. So let's take a look at what they do after here. Let me just read out the section right underneath this equation 24.1. The integration is performed along the path that Q follows as it moves from A to B. Right? A to B are the bounds of the integral. Because the force QE is conservative, this is an important word normally you hear in classical mechanics courses. For now, don't worry about it. Just remember that word conservative. The electric field is a conservative force field. Maybe you can just keep that in your mind. But if you don't, it's okay. This line integral does not depend on the path taken from A to B. So that's also an important thing. Doesn't matter if you forget it. It's okay. For a given position of the charge in the field, the charge field system has a potential energy U subscript E relative to the configuration of the system that is defined as potential energy equals 0. That sentence also, don't worry about it too much. But this next one is important. Dividing the potential energy by the charge gives a physical quantity that depends only on the source charge distribution and has a value at every point in an electric field. This quantity is called the electric potential, or simply the potential V. And they introduce it over here. V is equal to electric potential energy per charge, Q. Electric potential energy divided by Q. And again, you can see the original equation here and the electric potential equation down here. So I'm going to keep reading under 24.2. Because the potential energy is a scalar quantity, not a vector, electric potential also is a scalar quantity. The potential difference, delta V, is equal to VB minus VA between 2 points A and B in an electric field is defined as the change in electric potential energy of the system when a charge Q is moved between the points divided by the charge. So this is the equation we're going to get to. So keep in mind where this comes from. Basically, I told you change in potential energy leads to an equal and opposite change in work. Work is equal to force, which is Q times E in electromagnetism, times distance. And we also have that dot product and that integral to keep things kind of general. So now what they're telling you is we're going to define this new thing called electric potential. This is where the word comes from, electric potential. And since there is a delta over here, it is actually called, to be really, really rigorous with this, electric potential difference. And you can write this difference as the potential at point B minus the potential at point A. And it's literally equal to electric potential energy divided by some charge Q. And if you bring down this equation, which is exactly equal to electric potential energy, we bring this down over here. Let's do some math. It literally just cancels out this Q here, right? This Q and this Q cancel out because they're the same Q. This integral stays, this electric field stays, this dot stays, and this ds stays. So this is electric potential difference. And also sometimes, actually most of the time in circuit courses, this is called voltage. All right, so I've just introduced to you some of the theory. What does this actually mean? Well, you can think about it as the energy it takes to move a charge Q through some kind of electric field. It's related to the work, it's related to the electric field, it's related to the distance traveled and the direction traveled. But basically you can calculate it from this equation here. And I just want to remind you, you see what we've done over here? We've taken something and divided out a Q, and we get introduced to this new thing. Basically, the equation we have is this. Delta V is defined as delta U E, which is the electric potential energy, divided by some charge Q. This is very analogous, I'm going to draw a little curvy arrow over here, to defining the electric field as the force, maybe I'll put a capital E here, per charge. So remember we were introduced to Coulomb's law as this force here, 1Q times the second Q and the distance between them squared. If we divide this whole thing by Q, we define now a new quantity, which is the same equation as before, except just 1Q. And we define this as the electric field, right here. Now, we are given kind of this equation over here. Electric potential energy, maybe you can put the change in symbol there. And this is equal to Q integral electric field times displacement. And remember, these two together, Q times E, if you multiply this Q on the other side, you get the force, Q times E. So basically, this is a force over here. And because you have that, you have this is equal to force times distance, which is equal to work, with a minus sign over here. And since we have this equation, we are literally just given this. We can divide this again. Let me use blue. We can divide all of this again by a Q, and we can define this entire new thing as a new symbol. So this electric potential is kind of analogous to how we defined the electric field. I hope my equations here didn't complicate stuff too much. Now, what I wanted to do to end off this video is, well, basically I just introduced electric potential difference. I wanted to outline a couple things that, you should just keep in your mind. Electric potential difference is not electric potential energy. Okay? Electric potential energy has units of joules. My bad. You can equate it to work in this sense. And electric potential energy is equal to this equation. Force times distance. Electric potential difference, or voltage, this is how chapter 24 slowly leads into circuits, because this is a definition of voltage. Electric potential difference has this equation, which does not have units of joules. This is not the same thing as energy. The units of this guy are actually volts. So one final thing I wanted to leave you guys off with is using this equation, delta V is equal to delta U over Q. The units for this are volts. So that is the SI unit for voltage or electric potential difference. This is equal to joules, because in the numerator we have electric potential energy, which is units of energy, which is joules. And in the bottom we have charge, which is coulombs. Okay, very cool. And another thing is, remember from before how I introduced to you guys kinetic energy is equal to 1/2 mv squared? Or for example, gravitational potential energy is change in height times mass times gravitational acceleration. If you take a look at these guys' units, over here what we have is 1/2, which is unitless, mass, which has units of kilograms, and here we have velocity, which is meters per second, and then all of this is squared. So what this gives us is kilograms meters squared per second squared. And on the other side, kinetic energy is equal to joules. So you can see joules is can be written as kilogram meter squared per second squared. In this case, we have potential energy due to gravity, which is also energy. It has units of joules. On the other side, we have height. This is height, which is in units of meters, mass, which is units of kilograms, and gravitational acceleration, which is units of meters per second squared. So if you multiply these two meters together, you again get kilogram meter squared per second squared. So this is one way to write joules. So if we expand volts using this definition, we have in the numerator kilogram meter squared per second squared, right? All of this is joules, which is in the numerator. And in the denominator, what we have is coulombs. And then another thing I like to look at is Newton's second law, which relates on this side units of newtons, which is a unit of force, right? F equals ma. M is again units of kilograms, mass, and acceleration is meters per second squared. So newtons looks very similar to energy, except it is missing one m over here. It has one m instead of m squared. So technically, you can pull out this meter squared and have meters like that, and you can combine this into newtons. So you can write this whole equation into Newton meters per coulomb, which is again equal to volts. Let me just rewrite this here. So volts has all of these units. And let me see if there's one other way of writing this. Actually, what I wanted to show you was the electric field units normally are newtons per coulomb. This is from E is equal to KE Q over R squared, right? The units of KE are newtons meters squared per coulomb squared. You can check this out in a book, or the back of the book. In the top we have coulombs, in the bottom we have R squared, which is meters squared. So I'm trying to calculate the units for the electric field here. Coulombs and coulombs cancels, meters and meters cancels. So the electric field in the first chapter normally had units of newtons per coulomb. So if you take volts and you do volts per meter, you can basically cancel, well, you can rewrite volts in this unit or in this unit, but I'm going to just rewrite it in this unit down here to show you how the meters cancel. Newton meters per coulomb, and then we have another meters down here because I'm just creating this new unit, volts per meter. These meters cancel, and what we get is volts per meter is equal to newtons per coulomb. So this is one way of talking about the electric field now that is also introduced in the book. So you scroll down a little bit here. They show you that work can be written as Q times delta V. That is an interesting point here. Actually, let me read out this point here. Let's now consider a situation in which an external agent moves the charge in the field. If the agent moves the charge from A to B without changing the kinetic energy of the charge, the agent performs work that changes the potential energy of the system. Work is equal to change in potential energy. From equation 24.3, which is the equation up here, the work done on an external agent in moving a charge Q through an electric field at constant velocity is work is equal to Q times V. Interesting. And then they show you 1 volt is equal to 1 joule per coulomb. And then they show you that the electric field can be written in terms of volts per meter. The electric field is a measure of the rate of change of the electric potential with respect to position. And then they introduce some new units. So what I wanted to end off here, just to kind of piece all of this together, is in this next chapter, they basically calculate the electric potential due to various charge distributions. So here what they have is a constant electric field. So let's say we have some plates like this, and they are charged oppositely. In the first chapter, you learn that these plates create an electric field between them because the positive charge shoots out the electric field, and the negative charge is like the absorber of the electric field. So what we have here is the electric field, and we want to find the potential difference between these 2 points. Right, and the reason this is a interesting problem is because, well, first of all, this setup here is a capacitor setup. It's also the setup that very nicely creates a constant and uniform electric field. And also, the equation they gave us before, so for example, this equation here and this equation here, actually, we can just take this equation here. The change in electric potential energy is equal to the negative work done. Let's take both of these equations and just write them down over here. E is equal to negative work done. And also the new definition for electric potential, which is electric potential energy per charge. If we multiply both sides by this Q, then we can get an equation for the electric potential energy, which is literally equal to a charge Q multiplied by the potential difference. So this looks very, very similar to this equation. The force on a charge Q inside of an electric field E. Very, very similar equations. One thing over here times another thing with a charge Q multiplying inside of it. So I just want to show you how similar those equations look, but also if we use this equation here, which I introduced in the beginning of the chapter, we can equate all of this to the negative work done on a system. So if you have this equation over here, and you, for example, have the potential difference of these plates over here, then you can solve problems like if an electron is placed in a uniform electric field like this, how much work is done on this electron as it moves through this electric field. And that'll be probably one of the first problems I will help you all look at. But first of all, how do we find the electric potential in this region? Well, remember the equation that we've used is negative integral electric field dot ds. So they show you this in the book over here. Equation 24.1 and 24.3 hold in all electric fields whether uniform or varying, but they can be simplified in the special case for a uniform field. First, consider a uniform electric field directed along the negative y-axis. So an electric field like this. As shown in the figure below, let's calculate the potential difference between points A and B separated by a distance d, where the displacement S points from A toward B and is parallel to the field lines. So here they basically have VB minus VA, which is equal to the change in electric potential, delta V, or the voltage. And they use the equation negative integral from A to B, electric field, dot product, ds, the displacement. Then they just apply the dot product identity, which is literally this expansion here, A, magnitude of A, B, which is this vector here. Let's say this is vector A, vector B, magnitude of both these times cosine of the angle between them. And in this case, the angle between them is 0 because the displacement vector here is pointing in the same direction, right? They are going from A to B as the electric field. So cosine of theta here is equal to 1 because theta is equal to 0. You see now why I kind of took a little side tangent to introduce to you guys the work and how that equals to force times distance and how you can use the dot product there. So since in this case we have cosine of 0 is equal to 1, we literally just get integral of E dot ds. And since the electric field is uniform and it doesn't change over this integral, right? The electric field is the same everywhere. It is literally a constant. That's the definition of a constant. And then we can move the electric field out of the integral, as shown over here. Electric field comes out of the integral. And then this integral over here is integrating over ds, which again I told you were these super small components that you break down the distance in. But in this case, since ds is the distance here, and it is just a straight line, then the integration over the points A and B will literally just give you the total distance, which they told you in the problem was d. So this entire thing is equal to d, because again, they tell you that points A and B are separated by a distance d, where the displacement S points from A toward B. So this was the first and most simple kind of use of this integral. The integral that we got over here, which is literally the definition of electric potential, and they get to this simple equation. Delta V in a uniform electric field is E times D. So, okay, what is all of this saying? Let's go back to my example here. Let's say we have two capacitor plates, and they are separated over here by a distance D. We can use this equation here to calculate the potential difference in this scenario. Let's say we know what the electric field is inside. It's given to us. We can literally use the dot product identity to expand these guys. ds cosine of 0 degrees, right? Because the electric field and d, the distance, are pointing in the same direction. Actually, in this case, I didn't give you guys the displacement, like which direction the displacement is going. But if it's going this way, it is going in the same direction as the electric field. So basically what this is saying is, let's say this is point A and this is point B. This is point A and this is point B. But let's say we wanted to do it a little differently. Let's say we wanted to find the potential difference between point A over here and point B over here, just to have it a little bit different from the example in the book. In this case, the displacement vector is this over here. This is ds, technically. I mean, let's say the entire thing is equal to d, and in the integral, we break down all of these things into tiny little components, ds. Remember that originally we did ds, we broke things down in ds when we had a super wonky looking path like this, and it was beneficial to break everything down into little components ds. In this case, like I said, for a course like this in a like undergraduate physics course, you don't need to solve integrals with super crazy paths like this. You can just solve the integral, and if you know what the integral means, you can just basically add up all these things, and when you add up all these things, you get a distance. So no need to do any crazy integration. Let me write down this over here, and let me write down ds like this. So again, cosine in this case, since the direction of our vector A to B is going against the electric field, the angle between this and this is exactly opposite. So instead of it being 0 degrees, right here I will put 180 degrees. And if you remember, well, let's scroll up to check our cosine function, or you could just plug cosine 180 in your calculator. What we get is cosine of 180 degrees is equal to -1. So when the cosine function deals with vectors that are pointing perfectly away from each other, they are anti-parallel, then it spits out a minus sign. So this is equal to -1. Now let's rewrite this integral here. Actually, if we pull out the -1, then we get a plus sign over here. We get E ds. And remember, this E is now constant. That is literally the setup that we have. In other cases, this E might not be constant, and you won't be able to pull it out of the integral, and you'll have to do some kind of integration. By the way, this integration is from A to B. Those are the bounds we're looking at. So what we have here is E pulled out because it is a constant electric field in the setup that we have here. And we have this integral ds. So what this is telling you is add up all of the tiny ds components, let me use my laser pointer here. All of these ds components are how we break apart the displacement. In this case, it's kind of useless to break them up like this, because when you add all of these up, you literally just get the total distance d. So when you add up all of the tiny ds's from point A to point B, from point A to point B, you get the total distance, which normally should be given to you. So this whole thing is equal to d. And what we get is equal to E times d. Change in potential. Now, this equation is a little bit different from the one given in the book. The one given in the book is negative ED. And this is because what I did was I switched the vector right here. They were asking you for the potential difference if the displacement vector was in the same direction as the electric field vector. In this case, I chose to find the potential difference if the displacement vector was pointing completely opposite to the electric field vector. And as you saw, what I got was just a plus here as opposed to a minus. So how are these equations useful? Let's erase this one because this is the one that they used in the book. Well, take a look at this. We now have an equation for the potential difference across this setup. This is technically the voltage from this point to this point, delta V, and it is equal to the magnitude of the electric field multiplied by the distance separated by these guys. Very similar to a capacitor setup, which we'll take a look at in the next chapter. From that, what I can calculate is a couple things. Delta V is over here. I can plug delta V into this equation, multiply by Q over here. In this case, Q is not given to us, but technically Q would be a charge placed inside of here. So this charge could be positive, it could be negative, but it has a charge Q. If I place this charge in here and I multiply it by the potential difference inside of that, I can either get the work done on that charged particle, or I can get the potential energy of that charged particle. And if I have the potential energy, so let's calculate this kind of problem here. If I have the potential energy due to a charge inside of a potential difference, I can calculate the kinetic energy, I can calculate the work, and from the kinetic energy, I can calculate the velocity if I have the mass of the particle. So this is an energy sort of solution to find velocity or work done on a particle. So I know I've kind of spat out a lot of stuff here, but Basically, what I wanted to show you was all of the stuff leading up to the first part of chapter 24. Here they show you how you can calculate the potential difference inside of a uniform electric field. They do some problems. They show you here if the displacement vector was actually going from A to B across the electric field like this, then the work done and the potential difference would be a little bit different. So we're going to look at that in some other problems. And here they talk about equipotential surfaces, which is another very important thing that I don't have time to go into right now. The electric field between two parallel plates of opposite charge. This problem is something that I just started building up on in my notes. I also don't have time to go into it right now fully. But basically, they ask you to find the electric field inside of those plates, given the potential difference. And here they actually give you the potential difference, which is connected to a battery. So you can already see some stuff leading into capacitors and circuits and Ohm's law and all that. Here they have motion of a proton in a uniform electric field. So we have the proton, it is placed inside of maybe some capacitor plates like this. It's connected to a battery. Maybe it's just placed in a uniform electric field and you're given the potential difference across the points that it's traveling, A and B. Here they use the energy formulation to solve for the velocity. You can see how fast the electron is going, or the proton. And here they find the electric potential and the potential energy due to a point charge. So a point charge over here also has a potential energy. They solve it using the equation we just derived. And yeah, then it leads into some other stuff. So this chapter actually deals with a couple other problems. Electric potential due to 2-point charges. It basically starts the entire section of this chapter all over again. Remember this problem, except your task was to find maybe the force at point P or the electric field at point P. Now you're finding the electric potential at that location. Obtaining the value of the electric field. So turns out you can find the electric field if you are given the electric potential very easily, and it is basically taking a derivative. Here they show you some equipotential surfaces, which I'll get into maybe in a future video. And then we lead into the chapter that I was literally focusing on in the previous couple videos, electric potential due to a continuous charge distribution. Same thing as electric field, except now we have a continuous charge distribution and it creates an electric potential. So I'm going to end off the video here. I will do some of these problems here, but I just hope that what I showed you guys here was pretty useful. Again, it is quite crazy. The equations that we brought in, you may have never seen before. If this is the first time you're seeing it, maybe rewatch this video again. I know it might be a long video, but I hope that was helpful, and I hope I was able to, I don't know, teach you guys something new. So hope you have a nice day. Thank you very much for watching. Drop a like, drop a comment, subscribe. Thank you guys for watching. Peace.